Welcome to lecture 6, which has double lecture. If you survive this lecture, you're probably okay. Now, today there will be two kinds of people in this lecture. Those who are kind of up to pace, they understood mostly everything that's been said before, and they're gonna say, oh, that's a lot of stuff altogether, but I still kind of elaboration of the previous. And those who did not understand, they're gonna be a bit scared. Both of them can still make it, don't worry. We're gonna finish the exam well in advance for you to refresh everything. So what do we see today? We see the models limitation until now. So basically we look back into what we obtained up to last lecture, so sequence to sequence models or encoder decoder, what you want to call them, and the attention mechanism. And we see that, as usual, there are still some problems that we did not solve. There's always something better that we can do. And we see why we need something more. And then we see the solution, the transformer model. So this is still, as today, the most popular architecture in NLP. Whatever you are using even on the internet is very likely based on a somehow more fine-grained version of the transformer. It's still a transformer, whether it is an encoder decoder, a decoder only, whether it's an expert model, a reasoning model, the backbone is what we see today. And we see that transformers are super cool because they can parallelize the attention mechanism and they can explicitly model the order of the work they see. And overall, we see that they can contextualize the representation. So regardless of the sentence we see that we feed them, they find a way to disentangle the different meaning and obtain a good representation for it. So let's start with the model's limitation as usual. Let's start with a bit of motivation. Do we need a new model? So if you go back from lecture 1, we see many models that progressively address more complex problems. We augmented the number of parameters. We introduce a different kind of elaboration, blah, blah, blah. So we started with a multi-layer perceptron. Actually, if you want to be more precise, we started with a linear perceptron. Then if you add layers, it becomes a multi-layer perceptron. Very limited, was basically a toy model just to show us how training a model works. And it also has the issue that we have a fixed input sequence length. So we always needed to assume how many words, for example, would fit into it. What came after? Well, we had the RNNs. RNNs were a bit better because we now have a variable input length. But remember, the issue is that RNN was this cute thing that takes an input, takes a state, and produces some output, and then it rewinds and recursively reapply this. The problem is, this implies that if I want to produce an output, I need to get an input. So I can only produce as many outputs as the inputs I have. There are some hacky way, we saw the padding, we saw the end of sequence tokens, but it was still a bit of a dirty fix. Also, it does not work well on longer sequences. So we saw the encoder decoder, which is again just a very simple way to fix it. We have two RNNs. One is the encoder, which just processes the sequence, and then we have a decoder that keeps infinitely generating tokens until we generate the end of sequence, or we reach a termination limit. It's cool. So we have variable output length, and with attention, which is this thing that's every decoder state, look at all the encoder states, we also achieve better precision, better result on the longer sequences. So did we solve all of our problems? No. As I said, there's always another problem to solve. So we have, first of all, this issue that the memory cells still have a limited capacity. So what we said, right, this state vector has a certain amount of dimensions. It may not be enough to reliably recall information on very long sequences. Like we have this example that, do you want to memorize 2 words in a vector? Easy. You want to memorize 3 million of words in a vector? Is kind of a problem. Attention helps a bit, but it doesn't really solve the issue completely. Sorry. Word positions. We never really talked about the positionality, right? Because whether you change the position of the words also changes the meaning, right? So for each hidden state that we call SI, the current word embedding in a whatever RNN gets it's added to the previous state somehow. So, but since this representation depends on the input and we process the input sequentially, it also depends on how the words come to us, in which order, which means that RNN somehow keep into account the word order. It's internalized, it's not explicit, but we can assume that it happens. And in fact, if you give an RNN the same words but in different order, you will obtain probably different intermediate and final states. That makes sense. But it's sequential processing. If I have 3 million words, I need to do 3 million sequential steps to see what the state is at word 3 million, whatever. So it's slow, it's not great. Also, experimentally, even if you go to the best LSTM with attention, bidirectional, whatever, these still struggle to go beyond 4 or 8 layers. Keep in mind, layers, not steps. The we saw with the blue, sorry, too many emotions explained in NLP. So we saw with the blue example in the attention that we can go even to 40, 60, 80 tokens and the precision gets high. That's the steps. So we keep processing more and more words. This is the layers. So if I want the actual block of the RNN to have the very dense, many hidden layers, that doesn't scale very well. After 4 or 8 layers, it's a problem. So it's a problem to model more complicated nonlinearities, for example. And then we have the closed vocabularies, because so far we're assuming that one word is one vector. And this also carries the usual problem with polyphony. If I have one vector for base, my base is a fish, is an instrument, bank is the bank of the river, also the bank where you get the money, that's the problem. That's a real problem. So can we find a new model that still keeps tracks of the word order, reaches better performance than just sequential processing, so for example, it's faster, and contextualizing words, so we address polyphony? Yes, we can. But first, we start from a bit of recall contextualization. If you don't remember, we have this issue from lecture 3, I think, or the embeddings of polyphony. I just said that. So words has multiple meanings, but we are using one vector from one word. So this is a problem because we entangle all these different meanings into a single element. Contextualization is very important in NLP, and static word embeddings are not a good way to achieve contextualization. Do recurrent neural networks do this better? In a way, kind of yes. So we use this state, which is produced by using the previous state and the input, and then apply some kind of functions. You know, in an Hellman network is a little nonlinearity, could be a hyperbolic tangent, parallel, whatever. And each state acts as a representation of the sequence so far. So all the inputs we saw so far. So it's better than a single static word embeddings, but still not ideal because the state basically does two things at the same time. It is a summary of the whole sequence. Like if you have 20 words, the state is going to be the summary of the first word, the first 2 words, the first 3 words, blah, blah, blah. But it's also the meaning of the current word in context, because at that point we saw the left context. I mean, if you have attention, probably we can see also the other token, but still we need to sequentially process everything. So this does not change regardless how fancy you get with your LNN. If it becomes an LSTM, a bi-LSTM, blah, blah. So what about encoder-decoder? Well, we obtain relevant information from the current state. So for example, when we calculate, we have this state of the decoder, we can check at all the state of the decoder, of the encoder to obtain this attention vector, and we concatenate it or weight it somehow. So it's cool. We also obtain some contextual cues, because if we train over the attention, it's going to give a heavier weight to the words which are important into the context. So that's nice. But again, it's sequential. So we need to process first the whole input, and then for each decoder state, look at all of them. So what if I find a way to cut out this middleman completely and parallelize the entire process? So that instead of doing 1, 2, 3, and then we do all in parallel in one shot. That's exactly what we do with the transformer model. So say hi to the transformer model, which is by Vasvani et al. In 2017. You're going to see this guy for a lot of slides. What is familiar? Is there something that we can kind of see from the previous models? Something that we saw already? Yeah.
there's a decoder and encoder.
Indeed, there is an encoder and a decoder. It's not specifically marked, but yeah, the switch block on the left is an encoder, the switch block on the right is a decoder. But we also have a lot of different things. We have this thing called multi-head attention that you see here, which is what lets the transformer attend different words in parallels. We have this added norm, which is also called residual stream or skip connection, whatever, and a feed-forward network. So these are to keep the network stable and trainable, even if it gets very deep to a lot of hidden layers. And then we have positional embeddings that explicitly capture the order of the word. So a lot of stuff that we need to explain and cover. Oh, and also open vocabulary is not given here, I think, no? But we use BPE. We won't cover this because we saw BPE, I think, in the first lecture. If you don't remember how BPE works, then we represent, vectors instead of entire words as subwords. So that, for example, instead of eating, we have eat and ing. So we can use ing for eating, sleeping, studying, whatever. So we're not gonna check it today because nothing changes. Just know that the transformer model uses BPE instead of actual word vectors. But first, let's see what we gained from the sec-to-sec models and RNNs, and how we can improve it with the transformer. We need a lot of recall today to understand how we scale it. So remember this slide, this is the dot product attention scale. So we computed the dot product vector between the queries and the keys, scaled by the dimension in the dimension of the decoder. Usually it's also the same as the encoder because we want to keep it, easily transferable. Like, if I have a 3000 dimension in the encoder and 200 in the decoder, then I need another projection that learns how to conveniently transform it. Then we apply our softmax, so this becomes a probability distribution, and then we use this probability distribution as weights for a weighted sum of all the states, okay? So what are the query, keys, and values in the decoder attention? Does anyone remember, just in general, where they come from? Everyone's scared of attention. Okay, I'm gonna remind you. So this is what we have. Basically, reminding that these are arbitrary functions like neural network because we can combine these states however we want. The queries comes from the decoder. Basically, they're the current state of the decoder we're considering. The keys and the values are all the states of the encoder. So we keep looking at all the states of the encoder, say, okay, I have the cat sat. To produce the first word, how much should I care about the cat and sat? So the RNNs use the decoder state as the query for the attention. What if instead we use the input word representation directly? Now, that's exactly what the encoder, this guy here, in a transformer does. We have an input, and you can see that now the input is a bit different. So we have x that goes from y equals to 1 to n. That's the usual. We have n words, dec, sat, 1, 2, 3. We also have this L, and L means the word embedding in position I in layer L, because look at this guy, N. The transformer doesn't have only one encoder block, but he has stacked encoder blocks. So we can have 5, 10, 200. What does it mean? That every time we process somehow the input with the encoder, that doesn't go to the decoder directly. It goes to the second encoder. So we encode it again and again and again and again. So it's very, very deep. And you can already probably guess very, very heavy computationally, but we're going to see how it works. So the goal is to contextualize the word embedding. How the transformer does that is we transform each embedding into its query, key, and value with no need from, the decoder. We apply pairwise attention between all inputs. It means that every single word attends all the other words at the same time. And then we use the output, this result, as the output for the next layer, the next encoder. Okay, very generic. Let's see how this actually is done. So, okay. So every layer has its own linear transformation. that basically takes an input and transforms it into a query, key, and value, and then calculate the scale.product attention independently. So we have these three matrices that we can call WQ, for example, the matrix that produces the query at the layer L, the matrix that produces the key at the layer L, and the matrix that produces the value at the layer L. You can already see how much we're scaling the parameters, because if I have 10 layers, it means that I have 3 times 10 matrices that needs to be learned. So we're throwing a lot more parameters at our problem. We obtain the query, the query, the key, and the value by multiplying our vector by this matrix. Banally, this is just a transformation. And then we apply the dot product scale attention. So again, we will take key, Q, and V, we're gonna multiply them and scale them by the dimensionality and multiply by the value. This is just attention. Also notice there is this thing called massive optional. What does it mean? It means that for certain tokens, for example, the cat sat on the couch, we artificially set their softmax score, their score to minus infinite. And as a result, the softmax assign it probability 0. So if you try to plug a very, very small value, negative value to softmax, it becomes 0. We do this artificially, the model doesn't learn it, but basically for specific tokens, we hack the score to be very, very low. Why? Because for certain tasks, we don't want to see all the words. And now, you remember what was the problem in an RNN with padding? So if I want to produce 20 words from a sequence of 10 words, I keep padding maybe to 20. What was the problem? Why is a bit hacky padding? Yeah. Exactly. The pad token is not supposed to be learned. It's nothing. It's an empty token. So if we let the RNN do back propagation and change weights associated with the pad token, it's first of all it's useless because the pad token should be empty. Second, since the pad token will appear in many different contexts, it becomes a mess. So for example, the pad token should not be attended. So artificially, if a token is a pad, we set its score to minus infinite, a very small number, so that it never gets attended. Attention for the pad token is always 0. Or if we're doing text generation, we mask all the future token because otherwise we cheat. Like, if I have the cat set on the couch and to generate set, I look it on the couch, I'm cheating. If you do no masking, interestingly, this means that we see the whole sentence. So the transformer is in fact bidirectional. If we have the middle token, we can look at both the left and the right context. Yes?
For the test token, we also learn an embedding rate in the embedding matrix, so it also zero that one.
No. It's like it's 0, basically. It's artificially meant. I mean, I think so. Actually, don't know the implementation level. I don't remember. But if it's the matrix, it won't learn anything because we keep doing zeroing it out, basically. Should I? Yes.
Doesn't the encoder like put the input? So shouldn't we see all of the input? Like, why do we need to mask part of the?
We just said it because, for example, if part of the input is pad, because we may want to put padding for another reason, we don't want pad to learn anything. Or if you're doing text generation, you need to do what is called, we're gonna see it in the next week, but it's called autoregressive masking, where you can only see what you already generated. Otherwise, we are cheating. We're seeing the future, and if you're generating this pizza was horrible, I hate it, and we can see hate we were generating horrible. Yeah, it works, but the model doesn't learn. You probably can overfit and just take a shortcut learning, right? Now, the final output is our usual attention weighted sum, just the attention, and we are already parallelizing the process compared to what we were doing before with the maybe you can't see it now, but we're gonna have an example after I fill my bottle. So believe it or not, we are parallelizing. And if you don't believe, that's good, because as a scientist, you should always be skeptical. So let's see an example. Assume we have a simple sentence, the cat sat. It's 3 words, we are modeling it. For simplicity, I'm gonna completely ignore scaling now, because it's just a division. So I'm gonna ignore not doing scaling, and I'm also ignoring the final multiplication by values, because it's beyond the scope of this exercise. Probably you also will notice this is not necessary. So we have our input. Our input is 3 vectors. Of course, each row is a vector, which is, a certain dimension. Then here we call dm. Each word vector gets a key, a query, a key, and also a value, but now we're ignoring the values. So for example, Q is this X multiplied by WQ, and each row QI is this basically the vector, the actual vector multiplied by the matrix. So we get a query for the, a query for cat, and a query for sat. It's the same way we get a key for the, a key for cat, and a key for sat. Now I can just create this matrix by multiplying them, and you can see that I obtain the dot product of each single token, both with respect to each other, because of course we want to understand how that is important in the context of predicting that, for example. So the identity is gonna give you, every token in a function of itself, and the others with all the possible combinations. Now, each row answers a different questions. For example, if I take the first row, which is this guy here, so we have the cat and the set. Basically says, for the token the, how much should I attend the, cat, and set? So how important it is the itself, cat or set, to model properly the word the. And we're going to apply some softmax. So we're going to obtain, for example, 0.2, 0.7, 0.1, completely made up numbers. This means that to build the representation of that, I need to take 20% information of that, 70% information from cat, and 10% information from set. Because maybe in the context of this text, cat is very important. Parallelization comes here, that in another n, I will need to progressively, sequentially calculate what is in the state, the cat, set, blah, blah. In here, once I have this matrix, I can do it in parallel, because these are completely independent from one or each other. I don't need these to calculate these, I don't need these to calculate these. You see why? And parallelizing means your cores on a CPU, if you have a lot of money to waste, you can buy an AMD Threadripper, which is a CPU with 32 or 46 cores, I don't remember. Or you can have a GPU. And like, CUDA cores. Raise your hand if you know what a CUDA core is. See, not many gamers in here. So the main difference between a CPU and a GPU right now is that a CPU has a few cores but goes very high. It's not unusual to see a CPU going up to 4 gigahertz, which is 4 billion floating point operation per second or whatever per cycle. A GPU, like an NVIDIA 1080 on the other hand, has like hundreds of cores, but they run very, very low frequency. The problem is, if I want to do a matrix multiplication, a product, I don't need 4 gigahertz. I can do it in a split second. So the cool thing in a GPU that you can basically treat these CUDA cores as an array. They are basically a crazy big array. Load values and just multiply them instantly. So you can parallelize in a crazy easy way what you're doing. In fact, I think there is a famous example when CUDA programming came out that to do a matrix multiplication, I think on a CPU it took some seconds and it was like 500 times faster on a GPU. So that's how much you speed up. And that's why this works so well. Do you have any questions so far? Okay, then we're gonna take a bit of break. We refreshed our mind a bit, and I still have power from the double espresso I had after lunch, so we can go further. So we saw that we can parallelize the attention mechanism in a transformer, but we can scale up even more. So the intuition here is, let's say I have two tokens, they are relevant to each other, like cat and set, but in multiple ways, not in only one way. So how do I capture that? We compute attention multiple times at each layer. So we're adding even more computation. And this is achieved by what we call multiple attention heads. So you can see in these charts, it's better. You can already kind of guess what we're doing here, but I'm gonna show you anyway. So each head captures what is supposed to be one linguistic feature. Of course, we have no idea because networks are just numbers, but in theory, if for dead and cat, I calculate three different kinds of attention with differently initialized matrices and calculate different softmax, then I model different relationships with them, but they're still the same tokens. So in practice, we get our matrix K, Q, and V is already after the linear projection, keep in mind the capitalization. And we split it into H heads, which are linguistic features. And each head has a dimension which is basically dictated by the split. So you have Q, key, and V, which gone from being n times the m to n times h times the h. And of course, they must be divisible. So for example, if your vector has 10 dimensions, you might have two heads, each one with 5 dimensions, or 5 heads, each one with 2 dimensions. But you cannot have alpha dimension or 2 dimension and a half in a head. Each head computes its own softmax. So we are looking at multiple ways in which the tokens interact. And at the end, we concatenate the results and we obtain the final attention matrix. So I'm going to show you an example, very high level. So let's say we have three tokens, our usual data set. Each vector has 4 dimensions, very small, but good for this example. We have 2 attention heads, so we capture 2 linguistic aspects for each pair of token. And we have 2 dimensions per attention head. So we start from this, which is our query. So we have every vector, Q1, Q2, and Q3 has 4 dimensions. The trick is that if I split them and put them like this, I obtain a tensor, which is 3 times 2 times 2. So you can see that it has 3 rows, 2 columns, and 2 depth dimension, however you want to call it. This is not super relevant at the conceptual level, but it's basically how you do it when you optimize it in the GPU. That's how you actually allocate the tensors in your CUDA course. But it's not so important for you. But wait, now that I have these 2 slices, I can actually calculate the attention in parallel. And since I can calculate a different softmax, for this and a different softmax for this, because it's still 3 tokens, I can model different things. Then remember, GPUs are very good at parallelizing, so I can just allocate these and then do it in parallel. And at the end, I merge this and I calculate my full attention matrix. But that attention matrix doesn't contain a softmax calculated over all the 4 dimensions. Calculate the concatenation of multiple softmax. And in this case, it's only 2 heads, but imagine I have 10 heads. And for each token, I calculate 10 different ways it interacts with each different token. Then it becomes much more powerful. Yes?
I'm not sure how we're separating the interaction between the tokens because we have different tokens in different like slices.
We don't have different tokens, different slices.
Yeah.
These are the tokens. When I separate like this, I'm separating the dimension of each tokens, but there's still that cat set.
Okay, so the dimensions are different.
Yes, you're splitting the dimensions.
Yeah, sorry. Can you take a step back and go how to get those dimensions?
Oh, sorry. Give me a second.
Yeah.
What? I'm doing stuff. Sorry. How do I? Okay, that thing is gonna bother me for the rest of the lecture. That's simple. So how do we get our dimensions? That's our usual process. We define when we instantiate the transformer adding the dimensionality. I'm gonna say my vectors have 200 dimensions and they're gonna get trained. We still backpropagate to it. But now, when they backpropagate, this attention matrix is not a single softmax over 200 dimension, but it's many little softmaxes, depending on how much you split, that capture different interactions.
And one more question.
Yeah.
We only model the interaction between two tokens, like pairwise, not.
Yes, every time one token we do, every time we model the interaction of two pairwise. So yeah, if we have 10 tokens with 1, 2, 1, 3, 1, 4, 1, 10, then 2, 1, 2, 3. We also with itself actually. We actually model the interaction of the token with itself. So yeah, pairwise.
So like it gets difficult when we have like 3 different words that like constitute one single object that like starts like working words or.
Is that you mean polysemy?
No. I mean if we have like an entity that only exists, it will have like multiple words that can also be like singular words, not like New York. Like New York, we can like detect that.
Okay.
But when we have, I don't know, like that blue-green ball, and that gets captured like not very well if we are.
That I don't think I get your point, but no, actually, if I get your point, no, we capture very well because now we're modeling the interaction of each token with each other. That's contextual because every time you need to keep in mind those words and sentences are different. So that's how we model the context. Maybe we can discuss a bit more about this later because I'm not sure I get what you mean. Okay. No, give me a second. This circle is annoying me. Let me exit the. Okay. Oh, much better. Okay. Yes, sure. Sorry. From here.
Yeah.
Yes, that one.
This, I mean, we could still use the whole matrix, right? I mean, matrix multiplication was still parallelized also. Why do we split them into hands?
Why do we split if we can already parallelize them to multiplication? We are not splitting to parallelize. We're splitting to capture different things because before, when I didn't split, I had an entire softmax calculated over these 4 tokens. Oof. Oh my god. Right. Give me a second. I'm gonna show you. Yeah, we had an entire softmax calculated over these 3 tokens one time. Now we're splitting like even like this, let's say, and we're gonna collect 4 softmaxes, and those softmaxes predict different distribution of probabilities, not always the same. So when we remerge, we obtain a much richer representation. It changes the numbers, the amounts of the weights much more in different ways. You see right?
Yeah.
Keep in mind, now that I think about it, there's no guarantee that we may have a lot of redundancy in the end, the splitting doesn't help so much, but empirically it helps. It can also happen that sometimes the ads learn a lot of recurrent stuff. Depends how you initialize them, how you... Guys, see me, someone is talking over that. Guys. Thank you. So we've saw this. And now we can talk about more stuff, like the residual connection. So without seeing the specific implementation, you can already tell that there's a lot going on. We're passing the input through so many parameters, so many layers. We have 3 matrices per layer, and then we could calculate it multiple times by splitting. So intuition. Since we're doing so much stuff, it's better that our layer does not rewrite the inputs completely, the word embedding or the sub-word embedding, but apply a controlled update to it. And we do this with the residual connection or skip connection, or it has many names, but basically it's just adding the 2 vectors together and normalizing. So when we obtain the output of the multi-head attention, we don't replace the input with it, we sum them. So this is a double scope. First of all, and we normalize it. You don't need to understand how, if you can go back to the paper, which I think was introduced by Jeffrey Hinton, when they say exactly how they normalize, but it's a normalization, just keeps the values controlled. So you have 2 things to do. it stabilizes gradients because if you're always adding the basic word embeddings to the update, it's very hard to get a vanishing gradient. But also, if the model gives almost no update, because I don't know, we're starting training, so the multi-attention doesn't really know where to go. We get a very, very small change. You would obtain to completely rewrite the embedding with something almost empty. Instead, you're adding it to the base representation. So you're updating a vector rather than rewriting it every time. What else do we have? Yeah, okay, residual connection or skip connection. What else do we have? We have this little guy here, the feed forward. So the projection that we learn when we apply the attention, they're mostly a linear transformation and a softmax. If you recall from the lecture 3 or 2, when we saw non-linearity, that's not great because there's still kind of models kind of lines. So this doesn't let us learn meaningful partner. It may not be enough, let's say. So what we do is that we pass each token to a small neural network, which is called feed forward, because basically it just feeds, you feed the network across the network, apply some linearity, and then exit it out. And this has further non-linearity and teaches the model how to combine the learned information inside each token. And after this, we have another step of residual connection, because again, now we did another transformation and we want to update. So we sum it again and normalize. The intuition is that when we do attention, we mix tokens together, right? Because we're saying how then interacts with cat, how cat interacts with sat, and so on. But with the feed-forward network, we're taking one single token. So we're mixing the learned information inside the same token. So we're kind of elaborating first between token and then within tokens. Oh, yes?
I'm not entirely sure what values or where the values for a feed-forward come from and what they would be.
So where the values for the feed-forward network comes from is another small neural network that you initialize randomly and needs to be back propagated. It's part of the parameters of the model.
Part of the pre-training.
Yes.
Okay.
Yes. Okay. Okay, everyone super cool, understanding everything, or super scared about this. Okay, positional embeddings. So, as we said before, the RNNs learned information about positionality, but the transformer processes all the token in parallel. So this is completely lost because I have no context anymore of what comes first and after, because I'm calculating it in parallel. I don't have a recurrent step that gets done sequentially. So how do we do this? Do we go back to some sequentiality? We try something cool? No, we add even more stuff. So we use functions that depend on the position of the token, and the closer the tokens are, the higher the similarity of the functions. So these are called positional embeddings, and the first option is like using wavelength formulas. I'm not expecting you to remember this thing because I forget it the moment I stop looking at it, but if you plug some values into it, you realize that the lower dimension of a token oscillate very differently to the highest dimension. So if you have a word which has 100 dimension, the first dimension will gonna oscillate super fast, and the more you move, it's gonna go slower and slower. And the idea is that this produces kind of a barcode, because when you look at the whole sentence, it has specifically unique wave frequencies, and that helps you model the position. The alternative, if you're lazy, we make them another set of parameters and we learn them. So again, more parameters on top of everything. It's similar to the actual word embeddings. We randomly initialize them, and then we learn them as parameters. Which one should we use? It depends. Both have strengths and weaknesses, and I'm gonna be negative and focus on the weaknesses. The static one, well, the point is that you have the same vectors regardless of the task. So whether it is sentiment analysis, text generation, summarization, toxic hate speech detection, the position embedding are the same function. So it's a bit limiting. The learned ones, they break for sequences longer than those seen in training. Because if you're learning a matrix of embeddings, and you have basically a matrix which goes up to 700 words, the moment you get 701 words, it breaks. So you either need to retrain the model or to add the fake embeddings. That definitely doesn't work better. And he has extra parameters. How do we use this? We sum them to the input again. So you really see how we're constantly combining the input with the positional embedding, with the input of the multi-head attention, with the output of the multi-head attention, with the output of the feed-forward network, between all this kind of transformation. And just to give you a bit of a fun visualization, this is a visualization of the positional embedding. So first of all, you can see a whole sequence, right? That position, the first dimension of the tokens changes much more frequently. Like if you go here, for example, you can see how fast the position 4 and 7 of the embedding oscillates, which is even faster in the 0 to 3. When you go to 8, 11 or 12, 15, it becomes more like a smooth line. So that gives you something which is kind of a unique footprint of the tokens.
So,
Yeah,
One question is, how many words is this? Is this a whole sentence or?
that's a sentence of a bit over 120, as you can see on the, sorry, freaking magnet, yeah, token position and dimension. So in this case, you have something like 125 maybe, or whatever, 130 dimension and maybe 15 dimensions per vector, so to example. Okay. So there's nothing more to learn about the transformers so far. Keep in mind we're seeing only the encoder today, so there's already enough stuff. So let's do a wrap up of what we saw. So initially, the input is just a word embedding, randomly initialized. How do we contextualize? How do we account for polysemy? Well, during the training, what happens is that all this attention head learn how to transform the same ambiguous embedding into a context-dependent representation, because at every encoder level, you keep modeling how each token interacts with all the other tokens, and then that first elaboration gets fed to another encoder, which learn a further, more precise representation. Then you pass to another encoder, so you do those again and again and again. And after training, when you're just running the inference, the sentence passes across all these parameters. They kind of learns how to disentangle these and contextualize it, because they learned it from a lot of sentences from a pre-training corpus, let's say Wikipedia. Now you may say, doesn't an encoder decoder with attention do something similar? In the end, we're still seeking all the inputs, and I'll tell you, yes, indeed, this is not something new that only transformer does, but it's slower. This is all in parallel because one shot. It's hard to scale. Very deep networks and long-term context break even the best LSTM. But you will see with BERT, the model can scale to many, many parameters and many, many hidden layers. And also in the encoder, the states still accumulate progressive information. So at some point, it's less about the token and more about the whole context. So you may argue that the transformer does it a bit better because it keeps modeling token by token interaction. And this is the end of the first part. I propose we have a very democratic 5 or 10 minutes of rest, and then we're gonna go for the second lecture with BERT. Okay, cool. How was it so far? How's the transformer? Very complex, too messy, too much stuff? Raise your hand if it's too much stuff. I mean, it's not gonna change much. I cannot ask Google to change how the transformer works, but okay, raise your hand if everything was kind of understandable. Okay, that was kind of understandable. That's nice. Don't you get the impression that we're kind of hacking the problem? We're just, scaling until it works. Yeah, we're not. We're gonna have a specific section of the next lecture to show you that we're not. So today, again, we do a quick recap of what we just saw. So we quickly see again how the transformer works. Of course, focusing on the encoder because we saw only the encoder part of it. Then we introduce a very famous transformer model called BERT, which allows us to obtain pre-trained representation that we can use for other tasks. And then we saw pre-training tasks, so how BERT is pre-trained with two tasks that basically are both word and sentence representations. we see a performance deep dive. So what I just told you, quick reality check to make sure that we're just not, throwing more GPUs at the problem until it works. And finally, we see the fine-tuning, how we can fine-tune BERT beyond what is being trained on initially. So, recap of the transformer model, very quickly. We have this magical thing called the transformer. You give it an input, and it produces an output. If we zoom in into it, the transformer has an encoder and a decoder pass. The encoder encodes, and the decoder decodes. So let's zoom again. It's actually not one encoder, but a stack of encoder and a stack of decoders that encode multiple times and decode multiple times. And we saw that this is basically how they're made. Now, if we zoom again, we can see that like the encoder-decoder blocks are different. We're gonna see it later, so let's not focus too much on that. But you can see that the decoder has this field called single encoder-decoder attention, which is just a fancy name to say cross attention. Remember cross attention? Instead of looking at the sequence itself, we can look at another sequence to understand stuff about the one I am currently generating. One silly example is like, to generate the French token, I still look at the English word because I need to translate. But now let's go again our transformer encoder. We zoom it, we see that each block has this attention to contextualize the representation. The residual collection and the normalization that controls the representation updates and keeps the variance stable. The fit-for-door layer, which is once we have these features in the token, we combine them in a single token. And these, again, residual connection plus normalization again. I should also say we have the positional encoding, but you know it because you saw it like 20 minutes ago. And now we move to the BERT model. Oh, this is where things get exciting. The paper that everyone wanted to have written. I mean, also the attention is all you need and the transformer model. So the transformer encoder-decoder is really good as this task of sequence to sequence because it scales very well, as we already guessed, to many, many parameters and layers. It performs well along sequences. You didn't see, but I can tell you experimentally it does. It's easier to optimize because we don't allow the vector to change too much. So we have these controlled updates. And it's faster because it parallelizes the attention mechanism, which was the bottleneck before. But you can use it only for the task it was trained on, like pretty much any neural network. So what we're gonna do? Are we gonna retrain all those attention weights every single time? Are we gonna retrain all those positional embeddings every time we switch to another task? No. We apply transfer learning, which is applying the knowledge gained when solving one task to another one. And we actually saw it already in language model. Remember when we said, oh, we have word embeddings, now we can plug them into a network and further fine-tune them for a new task or just use them plugged with some other stuff. Can we apply this to the transformer to obtain what we basically are retrained contextualized representation, then we just use to another task? A rhetorical question, because if there wasn't a way to do this, we wouldn't be studying it. But yeah, there is, and BERT is a way to obtain this. So it's a very, very famous model by Google, at this point pretty widely known, as you can see by the amount of citation of the original paper. It has two variants, so there are two BERT models. In theory, now there are many more, but when it was released, there was BERT base and BERT large. And as you can include for the name, one is larger. It became state-of-the-art on various benchmarks at the time. This is one very cool thing, like, this is where you realize that something works in NLP. When you don't show that you improve by 2% on this specific benchmark, but across the board, all the famous benchmark on NLP, you become new state-of-the-art almost every time. It's very intensive to train it. At the time, Google spent 4 days of continued training on 6 or 64 TPUs, which are specialized hardware. It's not a GPU, it's not a CPU, it's a specialized kind of hardware made, which is very good for training neural networks. Today, we have even better ones. Today, you can take an 8 gigs GPU by NVIDIA and train it again in 4 days. Probably if you quantize or you do LoRa, other stuff, you can even do it faster. About the day, training for 4 days an entire model, it was a lot. So BERT can represent both words and sentences, introduces the fine-tuning task, and the point is our setup, that we start from a transformer and we want to obtain pre-trained contextualized word representation. For this, we need the auxiliary task, so this pre-training task for which we're going to train our transformer. And ideally, we want it to be unlabeled. You remember that the very powerful thing of Word2Vec was that we don't need to hire people to tell us. We just take the text, remove one word and predict it. It's naturally occurring. So we want something like that. So this actually anticipates what I say. Yeah, you remember the training goal of Word2Vec? I have a context, I predict the center word. If I'm talking about SQL, if it's skipgram, yeah, you partition and you predict each context from the word. You can go back to the lecture to see that. Now, can we use a similar task with a transformer? Because if we can, we now can obtain some pre-trained representation we can apply to any other task we want. BERT does this, and it does it with 2 different training tasks. So not like Word2Vec, we had only this one. We have 2 this time. And we're gonna see them now. First is called masked language modeling. Raise your hand, do you know masked language modeling? Yeah? Okay. Someone wants to tell me what's masked language modeling in short? Yeah?
I mean, yeah, you mask one word in a sentence and see if the model predicts correctly what the word is supposed to be.
Yeah, you hide one of the words and you ask the model, say, okay, what's this word that I hide? So the cat said, hide cat. Is it cat? Is it dog? Is it banana? Who knows? So the goal is this one. So you have an input sequence like before, and you mask an input token or more than one. We'll see there are actually more than one. You encode it with your transformer and reconstruct the masked tokens, asking to produce a probability over the vocabulary for what the token is. Now, each token has a predefined probability, which is 15% in our case, to be masked. So basically, each token, 50% of the has 50% probability of being masked, and when it gets masked, is not always in the same way. If we choose one token to be masked, 80% of the time is replaced with the special mask token. 10% of the time, it's replaced with a random token to teach the model that not only it can be masked, but you can also find tokens that are completely irrelevant, like the cat set becomes the banana set, and you should know that banana should not be there, even if it's not a special mask token, because again, this is like padding. We don't want to learn a representation of the mask. Also, it will be impossible. You can mask every possible token, so it will be impossible to learn it. 10% of the time, we actually do not replace it. Why? Because BERT must also learn that sometimes the token is just the right one. You say, okay, that cat sat. Are you sure it's cat? Yes, it's cat. So it's kind of this 3 times 3-way approach. And this is indeed your representation. So you have your model, you have this sentence that is an input, you mask some tokens, it could be more than one. And then at the end, you have your nice feed-forward network with a softmax that creates a probability distribution over the vocabulary. You may notice a special token, CLS, which some people call classification token. It's not relevant now, but we're going to see what it is in a bit. We're going to see it actually instantly because we have the second pre-training task. So the first one is done. It's just that we mask words and learn and teach BERT how to reconstruct them. The second one is next sentence prediction. So it's used to obtain sentence representations. What happens is that we have this special CLS token that we just showed, and it acts as a summary of the whole sentence. In our case, is actually a representation of the whole sentences, because what we do is that we have this separator token that separates 2 different sentences. So from our pre-training test, we have the cat sat, period, it's cute. So again, the cat sat, it's cute, put it with a separator token in the between and a classification token prepended to it. We sample two sentences, as we said, but there's a 50% probability that the second sentence is random. It shouldn't be there. And then we train token to predict via the CLS token if sentence one actually precedes sentence two. So BERT should learn that the cat sat, I cannot sit on the couch now, is good, but the cat sat, and that's how they won the Waterloo battle, is probably not a good example. It's a negative example. Sorry. And this again, a representation. You have your sequences. So you have the man, something to the store, penguin, something, are flightless birds. Again, so we are combining the two things. We are at the same time masking and then putting the separator and the CLS. So of course, we're gonna have the softmax at the token level when we predict if the token is masked, what the mask token actually is. And then we're gonna have another softmax 6 here at the CLS token level, which predicts a probability over only two variables, options, which is next or is not next. So to wrap up what we do in BERT, we take a corpus from Wikipedia, whatever, and we keep information on which sentences, the order of the sentences. We create our input sequence, which is the CLS token, all the tokens of the first sentence, the separator token, and all the tokens of the second sentence. We sample sentence one from the dataset, and with 50% probability, we sample another sentence, which could be the right one or a random one. Then we mask 50% of the tokens. Again, we follow the 80-10-10 split. So 80% of the time is a mask token, 10% is a random token, and the other 10% is that we don't do anything. We tell BERT that it's been swapped, but we did nothing really. We encode this input with the transformer, and we train at the same time on the two pre-training tasks. And these tasks affect how we learn the word representations, or some words in our case, because we're using BPE. So for MLM, we reconstruct the mask tokens, and for NSP, we predict if the sentences are successful. Successors. They don't work. Now, we're gonna discuss again this thing that I said before. So, oh no, before we have additional details, I don't even know my slides at this point. This is not exam relevant, but if you are curious about how BERT is implemented, we have positional embeddings. They're not sine or cosine waves, they're learned. For the next sentence prediction, we actually have a segment embedding, which is learned as well. What it is a vector of two rows, when each row is related to a sentence, and teaches the model, oh, this token is from sentence A, this token is from sentence B, because why not? Having more information to help BERT understand what kind of sequence is dealing with when there are two, of course. So he helps BERT to distinguish two inputs, and it's shown to help in tasks like question answering, natural language inference, tasks when you have two sentences. And also gives attention a signal, like does this token belong to sentence A or sentence B? The tokens are basically fed into BERT as a sum of the word vector, the positional embedding, and the relevant row of the segment embedding. So this triple sum, and then we keep encoding them. Another thing, the loss is a sum of two cross entropy loss. So since you're training on two tasks, you just sum them and try to optimize them. So you have one for the masked language modeling and one for the next sentence prediction. BERT has 12 encoder blocks in the base version and 24 in the large version. That means that once we get the cat sat, it gets encoded with multiple attention 12 or 24 times before we actually can go to the decoder. Not only, where we said we split, BERT has 12 attention heads or 16 when you go to the large. So every time we calculate 12 different softmaxes, for 12 times, while we still keep processing. Every time we normalize, we pass to a feed-forward network. So you can really see we're elaborating the token so much. And the hidden size, the word vectors of BERT has 768 dimensions if you're using BERT base, on 1024 if you're using BERT large. Total parameters, 110 million trainable weights and biases for BERT base, and 340 million trainable parameters for BERT large. I forgot to charge my laptop. Is there any chance someone has a Type-C charger here for a laptop? Plus 20 points of the final results. What is this? Adele, minus 20 points of the final results. Only worse than that could have been an apple. So, okay, thank you. Okay. But yeah, okay, so Simone, we have all these parameters, we real data token 3000 times. Does it work? Yeah, it worked. At the time of releasing BERT, you can see that we have some, these are like the baselines, the state of the art. There was the state of the art, how we call it, the highest possible performance before BERT. You can see the BERT already in the base version outperforms or matches very closely all of them in every single task. These are all QQP and QNLI. These are all different benchmarks. So in 1, 2, 3, 4, 5, 6, 7, 8 different benchmarks, BERT basically sets a new state of the art. So it works. But now again, we want to be skeptical and say, of course it works. We're getting bigger and bigger model. We have hundreds of millions of parameters. So of course it works. We're just stacking more and more stuff. Maybe it's a giant overfitting over the thing. Maybe, you know, it's just modeling everything. But no, I will argue we are not. First of all, because what we are discussing, multi-attention or positional embedding, it makes sense. It makes sense to have an embedding for position. It makes sense that we might want to model multiple ways in which the tokens are related to each other. But again, we don't go very far with it makes sense. You might think, Simone, okay, it makes sense, but I still, you know, I still believe that we move from a model with, like, I don't know, thousands of parameters, one with 100 million or something like that. So, and in fact, if you go back to the previous table and Google those baselines, the previous state of the art, most of them are extremely smaller than BERT. Maybe only the OpenAI GPT was roughly still 110 million parameters, but the others are like orders of magnitude smaller. So it's true, but at the time you could have believed it. But now let's consider things that came after BERT, but did something differently. 2019 by Facebook, we have Roberta, which is another model. He has roughly the same amount of parameters of BERT base. It outperforms BERT base, but uses more data, completely drops the next sentence prediction, and makes dynamic masking. Again, the transformer architecture works. This is a bit of a cherry-picked example because you can argue, okay, you dropped one of the tasks, but still a lot of parameters. Okay, let's go to 2019, this still BERT by Hugging Face. He has 97% of BERT-based performance, but only 66 million of parameters via using knowledge distillation. Knowledge distillation, we're not going to cover it now, but basically you have a big model, you distill the outputs and train a smaller model to imitate the bigger one. And again, you can tell me, okay, Simon, but you're cheating. We still have the big model. Maybe you're just, you know, bursting the big model, then kind of copying it somehow. Okay, let's go to TinyBERT. 14 million of parameters, 97% of the performance of BERT. Again, via knowledge distillation. You want another one? Albert, 2019, 12 million parameters, shared parameters across all layers. So which means that now every encoded layer doesn't have a different set of parameters, just share them. And still comparable to BERT base with now 10% of the parameters. So how come that we can keep shrinking it? Because BERT was the first thing that Google could do, right? So luckily, at some point, even they didn't know properly what was working and was not. In fact, BERT is overtrained, for example. It's shown that you can train BERT with much less data and obtain similar performance. So my solution, my answer is basically that, as you can see, the transformer architecture works. We don't need all those parameters because years after we matured, we realized that we can obtain very competitive model with a very, very small fraction of the parameters. But you can notice two things. That companies, these are all companies basically, they are making a difference because there are a lot of compute and the models are becoming much less understandable. So I forgot animation here, whatever. So what drives research? Knowledge and money. Typically, you have a lot of knowledge, knowledge. You don't have enough a lot of money. So if we knew that attention worked before BERT, how come that we have to wait for Google, right? Didn't someone tell, okay, let's just stack encoder blocks over, or let's just start to split it? The ideas are not so crazy, right? So the problem was not the knowledge, but the money. So Google has their own specialized hardware. So they trained BERT in-house, basically zero cost, while the university has to probably pay for this. So universities do not have TPUs. If they have to match it with GPUs, they would have need between 100 and 200 and high-end V100 or A100 CPUs, which means between $150 and $400,000 only to get started. But then what if I have a very rich university? Okay, then probably you need to use the whole cluster because I assume like this is already a huge amount of GPU, probably for to serve the whole university. So you have to ask all the departments, can you stop experiments for like, I don't know, 4 days if I'm lucky and I match the hyperparameters, the task representation. Otherwise, maybe for months for me to try retrain this model that, believe me, is gonna be so cool if it works. So probably you cannot do it. And if they have to rent GPUs online, the volume will be like $10,000, $12,000 per single run. So as usual, companies have money and money does cool stuff. Also, once we have enough compute, generally speaking, yes, bigger models work better. But the more you increase the size of the model, the less understandable it becomes. So can you actually see what is happening inside a model which has billions or millions of parameters? No, but that's why there is a huge topic which is explainable AI, which you actually see later in a later lecture. And you will see about it in the future, but it's a hot topic, how to actually crank open the transformer and understand what the hell those 2 billions of numbers mean together. For now, just trust the scaling and the core concept, but I can actually show you. Did I close the quiz? No, of course not. I can actually show you this very cool model, this website. This website actually shows you the model at the architectural level. You can also focus on something like where are the embeddings, or like what is the layer norm, where is the self-attention. Now, can you actually go here and tell me what is happening inside the model? I mean, of course, a lecture ago, we had the logistic regression, super intuitive. We switch the line of decision between the two classes, then the sigmoid with the curve changes that. What can you understand here? And this is GPT Nano, no, this is GPT-3 actually. No, bullshit. Okay, sorry. If we move to GPT-2 XL, which has a billion of parameters, it's even worse. If we move to, sorry, try to move to GPT-3, which is 175 billion of parameters, are you gonna tell me that you can go here? Yeah, I clearly see a pattern indentation. This is clearly polysemy, this is clearly verb-adjective relationship. So, yeah, that's why we now have a super cool model, but we understand very little about them. And with that, we can also almost move to the final part, but we're gonna have another quiz.
I have a question about the quiz.
Yes?
So the bigger the models, the more in terms of work, you just quantitatively, so it's just which bigger to look at, or is it quality?
So when the model gets bigger, it's harder to understand qualitatively or quantitatively. Well, how would you define quantitatively? Yeah, it is quantitatively because there are so many numbers, you don't really model it. Like, for example, you can turn a logistic regression into a decision tree, and depending on the model, it's also understandable. It's clear the patterns. You cannot do it with 100. You can do it, but it's not understandable. Yes.
Of the architecture in the website. Why do we have layer norm after like in the sorry, like before
Why do they have the layer normal after? Because that's another model. It's a decoder only model. Those are GPT models. We're gonna see them, but those are not BERT-like. BERT actually is an encoder only model. Oh, I forgot to say the BERT has no decoder. So don't know how I missed it. So finally, we see fine-tuning and variance of BERT. So now we have our model, we have pre-trained representation, it's cool, we set up new SOTA whenever, but how do we use it for new tasks? Well, there are many ways to use BERT. BERT is an encoder. So for example, for once it does not produce text, it just gives you representation. It's kind of like a very, very big, very, very cool word2vec. It can tell you a probability for the tokens. It can tell you if two sequences go one after each other. But it cannot do sentiment analysis, for example. It cannot do NLI. So fine-tuning is what we call this procedure, where we start from a base pre-trained model, BERT in our case, and we adapt it, is internal, not internal, representation, to a new task. We have various ways of doing it. The vanilla fine-tuning is that we add a decoder head to the model. We're gonna see in a bit what it is, but intuitively it's something that enables BERT to act as a decoder. So besides encoding something, can also produce text, for example, or labels. So you add this decoder head, then you train it. So that means that you have it on top of BERT and it has a matrix of weight. You get the input from BERT and you backpropagate and learn what basically teach this decoder head to do something with the input. Then you train progressively more layers. This is called freezing and unfreezing. So when you train the decoder head, BERT is frozen. You don't change anything. Then you unfreeze the last layer of BERT. So now the backpropagation trains the decoder head and the last layer of BERT. Then the one before, then the one before again. So you progressively change more and more weights into BERT. Or you can also do the entire network, like you just train BERT entirely, just maybe different learning rates per layer, so kind of dynamic learning. The alternative is adapter. When you add inside BERT, so we randomly initialize layers, but for this you'll see in a future lecture. We'll actually cover the adapters later. But what are decoder heads? They're basically randomly initialized layers, which are usually linear layers, which we add on top of the pre-trained model that then perform the downstream tasks. So for example, you can see here, you have BERT. It is like, let's stick to improvisation in this skit. You mask the model, blah, blah, blah. And this is a masked language modeling decoder head. So in a way, we were doing it already during pre-trained. When we ask BERT to encode this, and then we put it through a softmax and predict what the mask token is, that's a decoder head. It's just finalizing a task. But don't worry if this is confusing, because we're going to see how some of the most popular decoder heads. So let's say we're doing sequence classification, okay? So for a single sequence classification, what we do, we add a decoder head at the top of the model, randomly initialized. We model the entire sequence with the classification token that, remember, is supposed to be a summary of the sentence. And we use this token representation, its own word embedding, as the input to the decoder head. So basically, this decoder head gets trained on getting a sequence, a representation from BERT, and making some classification out of it. Alternative, if you don't want to use this single token, well, we can average all the tokens. Maybe we can have a decoder head which gets every single token representation. Maybe it averages, or maybe it does it only for the last 4 layers. Another sentence pair classification. So notice that now we have the separator. So we have 2 sentences and we want to classify. Maybe one is a paragraph, and one is the summary. One is the question, one is the answer. We want to basically give a label. We add, again, our randomly initialized decoder head. We encode both sequences with the CLS token, and we use this as the input to the decoder head. The same thing as before. This time, instead of having a label about a single sentence, we have a label of the pair of sequences, so it just naturally extends. What else? span extraction QA, which is we have a question and the answer must not be generated, but must be extracted from a context. So we need to tell them, yeah, the answer for this question in the text you tell me is from word 12 to word 20. So what we do, we add some specific vectors, which are called start of span and end of span vectors. We add them again on top of the model. We encode both the sequences and we train it with the objective of maximizing the dot product between the vector that tells me the start of the span and the actual token, which is the start of the span. How? I have some annotated data. So it tells me that the answer is from token 10 to token 20. So I'm gonna train these to have the highest dot product with token 10 and this one to have the highest dot product with token 20. Same for all the sentences in my data set. Then hopefully these two will become some general vector that can kind of understand when the beginning and the end of a sentence should be when being given a specific question. They say, oh, this is a question about capitals. This is a text that looks like talking about cities. Probably I need to, around here, it talks about capitals. So I need to tell you it's probably between this word and this word. Sequence labeling. Sequence labeling, well, I think at some point you will get in the idea of it. Add your randomly initialized decoder head, encode the entire sequence with classification, and use the token representation as input to the decoder head. So every single token now becomes an input, and your decoder head spits n labels instead of only one. So you're just changing the type of decoder head, really. But not only, these are fine-tuning, we can also variate the pre-training. So BERT is trained on the mask language modeling and next sentence prediction. But with time, Ivo proposed some variants of it. So we have token deletion. So we mask the token, but remove it completely. So we don't have any more 10 words and one is maxed. It just become 9 words, and BERT or whatever model you're training needs to understand that something is missing, in which position and what the token is. So you need to also understand that, oh, this sentence is too short. It should be longer. Text infilling, we mask multiple tokens with a single mask. So let's say that we have deep learning for natural language processing. Mask is a single token, but actually should become learning for natural language. So we learn how to unmask sequences of words instead of a single one. We're doing it before, but just by using multiple mask tokens. Now this is more dynamic because mask will be 1 word, 5 words dynamically. Sentence permutation. Basically, we take a sentence, we permute it, and then the model needs to understand that we need to reconcile. Oh, this doesn't look like the sat cat is a bit weird. It should be the cat sat. Document rotation. We basically rotate like it's a sliding window. So if you have the cat sat on the couch, the cat sat, and the model needs to understand that the model should actually be rotated to start. So you can see we have many different variants. Yes? How does the decoder work on text infilling? So in text infilling, well, actually, to be honest, I don't know how it works implementation because I never looked. One gut feeling could be that you could have the decoder generates multiple probabilities where each probability takes an input and precedent and probability. Otherwise, you could predict then something like that, for example. This won't be asked in the exam, don't worry. But we also have supervised pre-training tasks because as of now we have this thing. We take the text, it's given that he has some kind of self-supervised metrics, we change the order, we can already derive the label automatically. But if we have annotated data, then we get even cooler stuff. We can train our model like the C5, which is an encoder-decoder model. We'll show it in our next lecture. We train it to translate English to German. That is good. And the output should be das ist gut. Now we have an output. We can use teacher forcing, basically we can teach the model to do specific tasks directly from the pre-training. So just, if you have money, if you have the data, why not? So to conclude, I'm gonna give you a quick overview of what pre-trained language models you have. You have the encoder only, we just saw it, like BERT. The pro is that you have bidirectional encoding. So again, BERT processes everything in parallel. So for token in the middle, for example, you can calculate attention both with the left side and the right side. The cons of this model is that text generation is difficult. In fact, there was a whole wave of NLP research called BERTology, where we're trying to do all kind of stuff with BERT. And we could use BERT for text generation, but it was never really great. You have decoder-only models, which we'll see next time, and they are very, very good at text generation, especially autoregressively, but they don't have bidirectional encoding, so they only work left to right, or right to left. You will do one of those languages. And finally, we have both of them. So encoder-decoder, like BART or T5, they have bidirectional encoding, and they can make text generation properly. But they are very, very heavy because now we have double the amount of training, double the amount of processing. And that was everything I had to haunt your life with today. Reminder that you have to submit your homework, and tomorrow in the morning, the next one is going to be released. So have a nice week.